Hey guys, going to go a little farther with these rate laws. Some of this gets a little bit complicated, but most of it we can kind of just skim across the top because AP doesn't hit it too hard. What we're going to do with an experiment is we're going to gather data over time. This is how we're going to determine the rate of an experiment. And we can also determine the rate law based on a couple of different things that we can get from data. So when we're trying to determine the rate of a reaction, we're looking at the data from the chemical reaction. We're looking at how fast the reactants disappear. So as those go down, that rate, remember we're talking about the disappearance of reactants. So we can plot those data, just the concentration of whatever the reactants are over time. And that's this first one. And then we can take those data points and we can do the natural log of each of those concentrations that we gather and plot that over time. We can also take 1 over the concentration, the inverse of the concentration, and plot that over time. And if we plot these 3 graphs, this can give us an idea of the order of the reaction. It may seem a little strange. There's mathematical reasons why that we don't need to worry about. So if the concentration of A versus time is linear, okay, which it typically won't be, but if it is, we've got a 0 order reaction. Right? And I told you those are kind of uncommon. We kind of talked about those in the previous lecture. If the natural log of the concentration, if you plot the natural log of the concentration versus time, if that is linear, right? So you're just looking at which one of these is linear, then it's first order. And if the inverse of the concentration is linear, then it's a second order reaction. You know, you may be like, they may give you a graph. They'll just give you a graph and you have to look at the y-axis and you look to see which one of these it is. And if the graph is linear, that will tell you what order the reaction is. So you could either sit here and memorize like concentration is 0, natural log of the concentration is first, inverse of the concentration is second. You can memorize that if you like, or you can just look at your equation sheet. It's got these 3 equations on there. So in the section that says kinetics, this is all that's there. You have this equation that has just the concentration in a modified slope-intercept form. So you have the one that's just the concentration. You have one that is the natural log, and you have one that is the inverse. And they're in order. This is 0, this is 1, this is second, right? So 0 order, first order, second order. If you can't remember, look at the y-axis. It'll be one of these things. And which one of those things tells you which order just by looking at your equation sheet. Or you can memorize it, whatever you like. So if I look at this, here's my concentration versus time. Here's my natural log of the concentration versus time. And here's the inverse of my concentration versus time. And you can see that one of them is linear. The one that's linear tells you what order this reaction is. So I'm not even going to ask you to pause the video because you probably already know. This is a first order reaction because this one is linear. That's all you need to know. Here's another one. What order is this reaction? You don't even need to pause the video. I'll just wait a second and you'll go, it looks like it's second order, Mr. Powell. And you'd be right because this one over here is linear. See how these two have a curve? The third one is linear. The one that's linear tells you what order the reaction is. It's convenient to make these 3 graphs to determine very quickly what order the reaction is. And we'll do this with a reaction that we do in class. We'll plot data over time, and then we'll turn those into 2 more graphs, one with the natural log and one with the inverse, and we'll see which one is linear. And then we'll be able to find out what order the reaction is. This one's a 0 order. Like I said, it's uncommon, but you do see a 0 order. It's going down at a very steady rate, which is what we said is happening with the 0 order, right? There's so much that the rate doesn't really change much as it goes away. We can also determine K from the graphs. We just look at the slope. So in the case of the 0 order, right, it's negative slope, that's K. In the case of the natural log, it's also negative slope. And then for the inverse one, for the second order reaction, it's just the slope. And if you look at those equations on the equation sheet again, you can see if you could rearrange these into slope-intercept form, right, that's my initial value of the concentration of A. And so my initial value is that where x is equal to 0, and x is equal to 0 right on the y-axis, right? So that's our y-intercept. So we could rearrange this. We could make this minus brackets A naught, the original, right? Get rid of that. So now I've got y equals mx plus b. my y-intercept, right? So there's K. K is the negative slope. Same thing here. We're going to put this guy over here, just like we did before. That's our B from the y equals mx plus b equation, slope-intercept form. Hopefully that's all like, yes, yes, yes. We know this, Mr. Powell. It's super easy algebra from like 8th freaking grade. Same thing here. We're moving this guy. That's going to be B. In this case, there's no negative sign in front of the K, so K is the slope, right? This is the negative slope because it's got a negative sign in front of it. So these equations give us that and give us the ability to determine K from the slope. It's not very often you have to do that. You could if you have to, though. They will make it so the data points are really easy to spot. They don't line up great on this one. So we're not going to ask you for K here, but we will ask you for the rate law. And you should be able to do that once you have the order and the type of reaction. So this is decomposition of N2O5. So that's N2O5 turning into some stuff. Maybe it's just nitrogen gas and oxygen gas, who knows? But we know what order it is because my y-axis right there, that tells me it's first order. So you should be able to write the rate law. I think it'd be a good practice. Pause the video right now and try it. So I made that little pause the video blurb. I'm not sure if I'm going to keep using that. It's a little embarrassing. But the rate in this case is equal to K times the concentration of N2O5. And it's raised to the first because it's a first order reaction. It's the only reactant, right? Because it's decomposition. We know that's the only reactant. Decomposition doesn't include anything else. So that's our whole rate law right there. It's done. Piece of cake. And hopefully you were able to get that. This is a question I've asked you about 3 times already. You should probably already know this, but take a minute. I'm not even going to pause the video. Just take a minute. And the answer is higher temperatures, higher rates, because we get more collisions, right? And you have to be able to tell me both these reasons. AP will ask you why increasing the temperature increases the reaction rate. And you should say 2 things every time. 1, they collide more often when they're moving faster. 2, they collide with greater energy and are therefore more likely to be above activation energy. This is the Arrhenius equation. You don't have to do any calculations with this in AP, but you do have to be kind of familiar with it. And it is on your equation sheet, or at least I think it is. It used to be. So it's a way to determine what K is. This is just a constant. It's a pre-exponential constant. You don't have to worry about that value. Like I said, since we're not doing any calculations. So this is the E that we use in natural logs, right? This is, what is it? It's Euler's number, 2.71, right? So we're raising E to the negative of the activation energy divided by R, which is just, make sure that our units jive, and T, temperature, which is going to be in kelvins, of course. So you don't have to do any calculations with this. You could. It wouldn't be hard. You just plug it into your calculator. But what you do need to see is how K is affected by some of these things. So based on this, how is the rate constant? That's K. How is that related to temperature? Well, you can see what temperature is going to be like here. So this is going to be A over E to the, I'm adjusting for this negative on this exponent. So this is activation energy over RT. So this is E raised to that, but it's 1 over that. And it's multiplying that by A. So this is what K is. So think about what's going to happen. If I take temperature and I make it larger, then I make this value here a smaller value, which means I'm raising E to a smaller value. So this whole value down below is smaller. And if this whole value down below is smaller, then this entire value is larger. A over 50 would be a much smaller number than, say, A over 2. And so tracing through that, a higher temperature means a larger K, which is what we understand, right? Because a larger K is going to mean a larger rate. So raising the temperature raises K and therefore raises the rate. Temperature affects K, which is something I've said before. Also based on this, how is the rate constant related to activation energy? So if I look at that same thing again, K is equal to A over E raised to the activation energy over RT, right? There's my activation energy. As my activation energy gets higher, right, that's that hump we have to get over to make the reaction happen. That activated complex, the energy it takes to form the activated complex, that's activation energy. If that number gets bigger, then that makes this whole thing get bigger, right? And that makes E raised to the whatever get bigger. And as this gets bigger, then this whole thing gets smaller. So if activation energy goes up, then the K goes down, which should make sense because it's harder to get over that hump. It's harder to make that reaction happen. It's harder to form that activated complex. That's going to make the reaction slower. So increasing the activation energy would make it slower. Decreasing the activation energy will make it faster. And what can we do to decrease the activation energy? Well, that's something you could talk to your neighbor about. You don't even need to. You already know, right? How do we decrease the activation energy? Hopefully you remember that that's what catalysts do. They reduce the activation energy and make the reaction happen more easily, and therefore increase the reaction rate. And now we can see mathematically why. We did talk about 5 different factors affecting the rate of reactions. What are those 5 factors? They were in the first lecture for this for the kinetics unit. So take a minute, pause the video, tell me those 5. So here they are. They're the nature of the reactants, right? Depending on the nature of the reactants, the reaction can be faster or slower. The concentration of the reactants, the surface area of the reactants, the temperature, and then the presence of a catalyst. All of those things can affect the rate of reactions. Changing some of these things can change the value of K. Which ones? So take a minute, pause the video again. I'm going to play that clip again. Hopefully you remember from like 2 seconds ago, we just said catalysts affect it, and we said that temperature affects it. The nature of the reactants is not something you could change in a chemical reaction, but if you could, sure, hypothetically, I guess, yes, they would be, that would affect the reaction rate. Surface area is not really built into K mathematically, but surface area is absolutely something that is going to affect K. You could have a sample of a reactant that is in 2 different conditions as far as size of particles, size of chunks, one with more surface area, and that's going to have a faster reaction rate, and that's going to change K, because the only other thing you can change to change the reaction rate is concentration. So concentration of the reactants, that doesn't affect K, but everything else does. Think about our rate law. We have the rate is equal to K times the concentrations. If it isn't the concentrations, then it's built into K. At this point, we need to talk about half-life reactions. Half-life of a chemical reaction is basically the amount of time it takes for half of the reactants to react. Now, if you think about this, right, I've got this much reactant. In one half-life, half of it is gone. In the next half-life, the rest of it isn't gone. Half of what's left is gone. And then half of what's left is gone. And then half of what's left is gone. And eventually, you get down to like there's just one molecule and it goes. It has a 50-50 chance of going every half-life, so it's going to go pretty soon. So what types of reactions follow a half-life pattern of their reactants? And so these are first-order reactions. So they tend to be decomposition reactions. I mean, think about how you're going to get a rate law that ends up with an overall order of the reaction of being first order. Like, it's going to happen when you have only one reactant to have one on it. Or you can have to have some, if you have 2 reactants, one of them's going to have a 0 order impact on the reaction rate. So, and those I said are pretty uncommon. So to get a first order reaction, you have to have basically one reactant. That's almost always the case. So this is a decomposition reaction because that's what kind of reaction only has one reactant, is decomp. So half-life pattern, first order reactions. How is K related to the half-life of a reaction? Well, we can actually figure out. So a half-life is a period of time, right? It's the amount of time it takes for half of the reactants to go away. That's the time. So that is a value in seconds usually, but it could be hours, years, whatever. It is mathematically related to K. If you think about a first-order reaction, it's going to be linear, and it's going to be the natural log of 2, that gets to our half-life, over K. So the natural log of 2 is 0.693. So this is our equation, and this is right off your equation sheet. It's just like this on your equation sheet. The half-life So the amount of time it takes for half of this thing to go away, half of this reactant to go away, is equal to 0.693 over K. So you can find K if you have the half-life. You can find the half-life if you have K. What changes of conditions will change the half-life? Well, think about that list of conditions we were just looking at. How many of these are going to affect the half-life? And hopefully you can see pretty quickly that it's all of them except for the concentration, because it's all the ones that affect K. The only thing that affects the half-life is K. So concentration doesn't matter. Whatever you got there, half of it's going to go away in one half-life, no matter how long that half-life is. K determines half-life. So all of the other stuff, right, that is not concentration, those are the things that affect the half-life. Here's a typical half-life decay curve for a reaction. We're looking at N2O5 again. Here's our equation. Like I said, straight off the equation sheet. We don't need to worry about the natural log of 2, just 0.693. That'll get us there. So you can see we've got a certain amount at this time 0. At one half-life, 24 minutes in this case, there's exactly half of the amount of the reactant. After another half-life, another 24 minutes, so 24 plus 24 is 48, so 2 half-lives, we're at a fourth. Then we're at an eighth after 3 half-lives, right? So 1 half-life, we're at a half. 2 half-lives, we're at a fourth. 3 half-lives, we're at an eighth, right? So we're just cutting it in half every time. 16th, 32nd, 64th, etc. So you should be able to do this practice problem. Go ahead and pause the video, do this one, and do this one. So do these next 2 problems. Then I'll come back and show you how to do them. Okay, so hopefully you've got answers to these, but let's go ahead and do them. I don't have my calculator. If I've got 4.6 moles of a certain compound, decomposes to 2.3 moles, so that's 1 half-life, right? So that means the half-life is equal to 82 seconds. How do I know that? Because I went from 4.6 to 2.3. I got cut in half. Like, that's 50%. So if this is a first order reaction, what's the rate constant? So I can find K. I know that the half-life is 82 seconds. So 82 seconds equals 0.693 over K. Solve for K. 693 divided by 82 equals. So it looks like K is equal to, so we've got 2 sig figs, so 0.0085. And the units for this are going to be 1 over seconds, which should make sense if you think about it. What are the units for K? It would be this, 1 over molarity, order minus 1 times seconds. And in this case, it's first order, so order minus 1 is 0, so it's 1, so it's 1 over seconds. It's always going to be 1 over seconds for a first order reaction. It's always going to be a first order reaction for a half-life one, so it's always going to be 1 over seconds for a half-life problem. Under what conditions would you make the reaction have a different amount of time as its half-life? What could you do? You could change the temperature, you could change the surface area, you could change any of those things, but not the concentration. Cyclopropane, kind of a cool little molecule, kind of an unstable little molecule. These are some tight bond angles, baby. 60 degrees is nuts. So it does not want to be like that. The rate constant, so this is K, is that. So what's the half-life of this reaction, of this being converted into this? It's just going into a more stable version. So all I have to do is say that the half-life is equal to 0.693 over 9.2, 1 over seconds. Do a little calculation, and we get the half-life is 0.075 seconds. How long does it take for the concentration of cyclopropane to reach 1/4 of the initial value? So 1/4 is 2 half-lives. So 2 half-lives is 2. 1 half-life is this, right? 1 half-life is that. So 2 times 0.075 equals 0.15 seconds. All right, all I did is multiply by 2, because to get to 1/4, it's 2 half-lives. 1 half-life gets me half, another half-life gets me 1/4, so 2 half-lives. 1 half-life is 0.075. How long is 2 half-lives? That's an easy math problem. Just multiply them by 2. And 75 and 75, hopefully you know that's 150, so head math, right? No calculator necessary for that bit. There's our answer for that. So that's kind of integrated rate laws, kind of the next level of where we go with rate laws. I know this lecture is a little short. I'm going to give you some mastering problems. You can do those. I wanted to give those to you in enough time that you can take your time getting through them. Remember, we are going to have a test over the reactions unit shortly after we get back from after Thanksgiving. And then we'll do a lab and a couple of other little things. And then we'll take the test over the kinetics unit. So we got 2 tests we're going to do when we get back. You guys are doing great. Hang in there. So this is the Arrhenius equation. This is the Arrhenius equation. Gosh darn it. This is the Arrhenius equation. Arrhenius equation.